Okay, so for the last talk, I have in mind two things. One is that we're going to give one more example of theories with one-form global symmetry, with higher form symmetry, not in 4 space-time dimensions, but in 3 space-time dimensions. And then later, we'll do one application, which is to the phase structure of SUN Yang-Mills theory. Okay. So what's the last time we had 2 examples, abelian and non-abelian gauge theory, of theories with one-form symmetry. So another example of a theory with one-form symmetry is 3D Chern-Simons theory. Okay. So let's start with U1. Okay. So I claim that this has ZK one-form symmetry. What are the symmetry defects? They're just the Wilson lines, where n goes from 0 to k minus 1. So they're just the complete set of Wilson lines. Alternatively, you could think about this symmetry as coming from a symmetry of the action. The action is invariant. The action k over 4 pi a wedge dA is invariant under shifts by a flat connection, under shifting a to a plus 1 over k times epsilon, where this is some U1 flat gauge field. So we saw a similar thing also in 4D, that shifting the connection by a flat connection was generated by a one-form symmetry. Here it's discrete though, so it's a ZK. And what are the charged objects? Well, the charged objects are just the same lines themselves. So of course we know that in this famous braiding relations in abelian Chern-Simons theory. So if this is the Wilson line of charge n, and this is the Wilson line of charge m, they have this braiding. Okay, so charged objects are the same Wilson lines. Okay, let's try and dissect that statement a little more. So remember what it means.
Yesterday there was the shift with the delta function as well. Is there a delta function here?
There's no delta function. The delta function was related to it being continuous. Yeah, here there are just, you're asking me about the spatial dependence of this epsilon? Yes. Let's see, I think that right, so saying that it's flat modulo gauge transformations probably makes the parameter space discrete in this case. Let's see, so if we
if I think it's a charge operator generating it, the charge should only act on that line.
Oh, you're right. Sorry, you're right. Yeah, no, you're right. Right. I mean, I want this shift to generate holonomian A, which is Poincare dual to where I put the symmetry defect. Right. So that's right. So if this is a flat connection, I mean, we can go back to this picture. If this is a flat connection, well, I guess I'd want to turn it the other way. But if it's a flat connection whose holonomy, say this one is the one whose holonomy I'm trying to shift, then I'd want to put the symmetry defect here at the center, like yesterday. Again, you can think of this as coming from a disorder defect, where we modify the holonomy in codimension 2, or we modify the connection in codimension 2. Okay. Good. So I want to unpack this statement, which is that the charged objects are the same Wilson lines. So let's think about what it means to gauge a one-form symmetry. So what it means to gauge a one-form symmetry is that we sum over we sum over insertions of these symmetry defects. But here, so that would mean we would consider configurations like these. We tried to make them equal because we're summing over insertions like that. But here we see there's a phase. So there would be some obstruction, that means, to gauging the one-form symmetry. So this means that there's an obstruction. Gauging the one-form symmetry. And that means that this one-form symmetry has an 't Hooft anomaly.
I didn't understand the first bit. Can you explain the big obstruction?
How do I see it? Well, so let me put it this way. I want to sum over configurations where I insert different symmetry defects. But the effect of this this phase relation here, since these configurations are charged, is that, if you like, summing over all of these phases would make the partition function vanish. Alternatively, maybe a different way to see it is that since these lines have non-trivial braiding, which is what this is telling us, there's an obstruction to doing topological manipulations of them. We get phases when we do topological manipulations of them. So remember that topological manipulations of the lines were the same as gauge transformations for the background gauge field. And here we're saying that topological manipulations are giving us some phase.
You're saying the summing over them is not an unambiguous description?
It's not that not only that it's not it's not, we can't do it in a way that's gauge invariant for the background two-form gauge field that we like to discuss. So this braiding phase is telling us that there's some failure of gauge invariance for this background gauge field.
Yesterday you said that if you tried, in 4 dimensions, you tried to gauge both the electric and the magnetic guy, there was some issue. And the fact that this guy is charged both electrically and magnetically.
That's it. Yeah.
Right?
Yeah. That's the point. Yeah, that's a good way of saying it. So this is kind of very basic point that. So physically, what's happening is that what's the slogan here? The braiding of abelian anyons in Chern-Simons theory is the same thing as the one-form Hooft anomaly. Yeah, how do you think of it as inflow? So, so we have a ZK one-form symmetry. So there's a two-form background field, which is valued in ZK. That's the first thing. That's what the background field is. That's the background gauge field. And the inflow action will look essentially like this. So we'll integrate over some 4 manifold x4 b cup b, where this is, and there'll be a number here related to the spin of the generating anion. So there's some generator of this decay. It has some spin. There'll be a number that is proportional to that. And then we'll have essentially b squared. This makes sense for discrete gauge fields. And it's gauge invariant for discrete gauge fields. But everything is flat. So that's what the inflow action would look like. This cup is the discrete analog of wedge. Okay, so right, so if you wanted to know in 3 dimensions, so this is a useful thing to remember. In particular, if you have some Chern-Simons matter theory, it may have some subset of abelian anions that obey abelian fusion rules. And those will give us one-form symmetries. And their braiding is an RG invariant, their braiding matrix.
These anions are dynamical anions now? Or lines?
I'm imagining lines. So just as in the 4D case, if I had had U1 level K with matter that was charged, say of unit charge, I would break all the one-form symmetry.
So same here. So if you took unit charge, matter with unit charge,
There's nothing, right? But if it has multiple charge, there will be something. Yeah, there will be something, and then the fusion of the remaining line, that the braiding matrix of the remaining line is an RG invariant. Okay, this is not particular to
in particular SU and Chern-Simons theory with fundamental matter
has nothing. That's it. I guess you can leave now. Okay, good. So this is not particular to U1. Let's also do some non-abelian Chern-Simons quickly, just to see an example there. So how about SU2 level K, Chern-Simons? So this, I claim, has a Z2 one-form symmetry, again related to the center of the group. In Chern-Simons theory, not all of the one-form symmetry comes from the center of the group, but in simple cases, that's a way to identify some of it. Okay, so how do we see this? So there are lines with spins less than or equal to 1/2 of the level. So the allowed Wilson line spectrum gets truncated. So we look at, so we should first look for what's the line in this topological field theory generating the one-form symmetry. And it's the one of maximal spin. So the symmetry defect is the line of maximal spin. K over 2. So let's look at a line of spin J, and let's braid the spin K over 2 line around it. What do we get? Well, we get -1 to the 2J times the line J, which is one of the elements in the solution to SU2 level K Chern-Simons theory. So if J is a line of half integral spin, we get a minus sign. If J as a line of integral spin, we do not. And that's why this one-form symmetry is associated to the center. It's measuring how the representation carried by J transforms under the center of SU2. Okay. Yeah.
Suppose like the last, let's say you said something about the symmetry defects being topological. When I was asking what makes something a hypothetical component, you said different topological defects.
Mm-hmm.
Right? But in this case, those remain topological, right?
Yeah, so it's also the second item on my list was there was topological, and then there was the fusion algebra, the abelian fusion algebra.
Fusion algebra, or just the fact that one can move to the other?
So, okay, let's say it just in the language of Chern-Simons theory. So there are lines everywhere, as you said. So how do I identify which of them are one-form symmetry defects and which of them are just some other lines in the theory? So the first thing is that when it braids around any line, it should give us a phase times that line. Right? We want to say that it assigns a charge to the line that it braids around. And the second thing is that if you take two of them and you fuse them together, you
Not the canonical case need not be the identity.
what does that mean?
Need not be that the particular representation will be given under the form. It could act on the case of the symmetric matrix, and then that's the charge.
No, but it's abelian, so it's all one-dimensional representations. Just assigns a phase to all the lines.
I think it's the same. In some basis that may always be.
It's some basis.
Some basis of the other basis.
The charge of this would be linear combination.
I don't think that is possible. Let's see if we can say why.
Because all the defects are abelian,
Yeah, I mean, if I put two lines here, and I say that I braid around this to get two lines over here, can't I just pinch the middle and say that individually I have to get the same phase on each of them? I think I can.
Need the direct sum.
The direct sum.
That is the product.
What I said was the product. Okay. Let's see, you want me to put a direct sum representation on a single line? But I still think that I should be able to make an argument that it just has well-defined charges on all the individual lines.
Is there some way of taking out between linear combinations of these? I mean, the representations of this is maybe some of it is the question.
But the line operator is form basically in this case, no?
I don't think there's a meaning to linear combinations with general coefficients. There might be a meaning to R1 plus R2 with coefficients 1 by putting direct sum of the representation on the line. Okay, I don't think it can happen. I think it has to be in the standard unit line basis.
The algebra should be abelian, and then you can diagonalize that.
But I think you're again sort of asking me sort of why it can all be done in the same basis.
I think the question is take J plus J minus 1. He's going to make a basis which is J plus J minus 1 and J minus 1.
Yeah.
Then this is not diagonal in that case.
This is not diagonal in that basis.
So you want to know why is this J basis? I mean, the representations
The irreducible, I mean, we can we can define what they are physically by just, computing the Hilbert space on S2 times S1 with one line wrapped around. But still,
So let me, because k by 2 symmetry, right, use this model k by 1, 2, then
it doesn't always give a number of modulus 1.
but resolve that line.
That's a slightly different question. The fact that this happens is a semi-classical fact that the k by 2 Wilson line generates a rotation by 2 pi in S2.
Mm-hmm.
So that's why it's this nice. It's basically the center element.
Yeah, yeah, yeah. Let me think a little bit more about your question, see if I can come back to a better answer. Okay, but so the properties that we would want are that, first of all, when it braids around any line, you get a phase times that line. And second of all, that they obey abelian fusion with themselves. So one form symmetry defect 1 times one form symmetry defect 2 fuses to give you one form symmetry defect 3.
So this abelian argument came about when we discussed the fact that there is this one form symmetry which is reflected like this, and then there is this thing which can move around.
That's what makes it commutative. But to say that they fuse to give you a unique line is a strong statement.
I thought we were just arguing for the community.
No. I'm saying that UG1 times UG2 is UG1 G2. The fact that if you fuse general lines, in general you'll get a sum of things over here. The one form ones are characterized by this property. In condensed matter, they're sometimes called abelian anyons, which is why I use that phrase.
So that would be the basis of any. The operator, let's say, I don't know, you here I think this will work for it, but there is this one form symmetry. If I just, my theory, I want to identify symmetry of it. You have UG1, UG2, and I call whatever I just say UG1, UG2.
Sorry, what?
Part of definition of UG1, UG2, how does it define the okay.
So there have to be as many symmetry elements. Each of there has to be some symmetry element in your
Yeah.
form symmetry. You have to identify all the line generators. That forms a group, and it should close.
It's close.
In this case, it will just be two identity.
That's right. Yes. It'll be 2 of the k over 2 guys fusing to be the identity. Maybe let me say something which might make you happier in Chern-Simons theory. I think you can use modular invariance to replace these two things by saying that a line is a one-form symmetry generator. It's called a line U. If U times L is equal to some fixed L prime for all L. So here we put in the fact that everything was a one-form symmetry generator. But here now I mean that L could be anything, and I get a single element in the fusion on the right-hand side. So let me show you what I mean in this example. So the fusion algebra in SU2 level K is known. So
I guess the statement is that in general these operators will form a ring. If you want to
I want to make it group-like. Yeah, exactly.
And that is integrated.
Yes, but I'm doing something else, which is I'm replacing. I'm saying that you can replace the criterion that these braid around something to give a phase with the criterion that their fusion with anything gives you a unique thing on the right-hand side.
But that anything is once again a particular representation.
No, but this L has to range over all the lines in the theory. Let me show you the SU2 example so you see what I'm talking. Okay, so let's suppose we have two spins, L and L prime. Okay, so this, there's the Gepner-Witten formula, which says that this is a sum over spins J, where J goes from the difference to the minimum of the sum and K minus the sum. Okay, where J is in steps of 1. So this is half integral notation. These things can be half integral, but J goes in steps of 1. So notice if K is enormous, this goes off to infinity, and then this just becomes the representation ring of SU2 as expected. But for lines whose spin get close to K, there's some interesting truncation. Oh, I didn't mean to erase that. Oops. Okay, so let's look at what happens when we take L, let's say L prime equals K over 2. Okay, so then we see that K over 2 fusion with L is what? So J starts at K over 2 minus L. But the minimum here, so this is K over 2 plus L, but this is K over 2 minus L again. So this is equal to the single line K over 2 minus L. So this was the property that I meant. The one-form symmetry generator, fusion with any line in the theory, gives you a unique other line. So you can using this, you don't have to check this. If this is true, this will also this braiding phase property will be automatically true.
And the line can't be 0.
The line can't be. It could be the identity. The identity.
It could be nothing. It cannot be nothing.
Does nothing mean the identity
No,
line?
nothing means nothing. Meaning in SU2,
Yes.
you always get either one representation or 0.
Or 0. When do I get 0 representation?
Yeah, maybe it's 0. Oh, sorry, I'm saying the 3-point function. You could get many.
Yeah. Okay, so this is in topological field theory. This is if you have a solution to the fusion algebra, this is a fast way to identify which are the abelian anyons. You look at which of them have the property that the fusion with anything gives you a unique other thing.
Here I can ask a question a little bit.
Mm. Figure out this question. I still don't have a good answer to it, but I will think about it. Okay.
So I just want to say how I'm understanding this, at least in the case of SU, probably semi-classical.
Mm-hmm.
You know, Wilson line semi-classical can be thought of as being represented by what the similarity, up to similarity transformations, what the conjugacy class of the column means.
Mm-hmm. Mm-hmm.
Right? So you go around the Wilson line, you pick up some polynomial which lies in your group,
Mm-hmm.
and the Wilson line tells you the conjugacy class of that.
Yes.
Now, generally speaking, if you know the conjugacy class, you know the group element only very imperfect. Because you can take the group element of similarity transform. And so, taking that and compounding with some other conjugacy class gives you lots of representations. Because depending on relative orientation, you can get different rotations. But in the case of SU2, there's precisely one rotation quantitacy class completely determines the rotation. Namely, the rotation by 2 pi.
Because
the
it's
rotation
central.
by 2 pi in any direction is the same.
Because it's central in the group, so
Because it's
continuity
central, right.
preserves it.
So it's all the axis minus 1 on each.
Mm-hmm.
Okay? So basically, combining it together with other things gives one thing. Because it's just one thing. Okay, so that and that is the same, very similar thing. But once again, the fact that you just go through is this continuity class in central.
Mm-hmm.
So this makes it sound to me that in SUN also your continuity classes will essentially be the center.
Yes, I was about to say that. Yeah, yeah. So for before going to SUN, let me say, let me actually comment on the anomaly in this theory. So again, we could now plug in J as K over 2 here and ask if there's an interesting braiding phase among these abelian anyons. And there is if K over 2 is odd. So based on the discussion we had before, we say that if K over 2 is odd, there is an anomaly in this one-form symmetry. How can we think about it? Well, we discussed yesterday that gauging the one-form symmetry is the same as performing, when it's associated to the center, is the same as performing a quotient on the gauge group. So gauging the Z2 one-form symmetry takes us to SO3 level K. But in SO3, there's a different quantization of the Chern-Simons level because there are fractional instantons. So in SO3, fractional instantons imply that in these normalizations, K must be even. So this is why the anomaly hits you in the face, is because there just is no Chern-Simons theory, SO3 level K, in these conventions if K was odd. Okay, good. So let's now do some brief comment about the SUN generalization. SUN level K. This again has Zn one-form symmetry. Again associated to the center. And it's easy to say what the representations are. So the generator, let's call it U1, is this symmetric representation on K boxes. And okay, it continues. So U, this will be capital N, let's call it L. K is a square tableau, which is L by K. Okay. And everything works very similarly. So for instance, the braiding of U1 around U1 is e to the minus 2 pi I K over N times U1. So again, we see that there's an anomaly because there's a braiding phase in the generators of the one-form symmetry. And that's again consistent because the quantization of the Chern-Simons level in PSUN is up by a factor of n. So the Chern-Simons level in PSUN would have to be a multiple of n in these conventions for it to be consistent.
PSUN is SUN mod ZN?
Yeah. And also, we can again look at this fusion property that I was advertising before. So U1 times a tableau of any shape. It's simple to say what it is, so it gives you a unique representation on the other side where you first add this thing of length k to the tableau. And then from here, you just delete any columns of length n. So this fusion algebra gives you a unique thing on the right-hand side. Okay, so sometimes, although I didn't come prepared with any examples, it's sometimes true that the one-form symmetry is not associated to the center. It can be more interesting, but whenever you've got a center about, that's a good candidate for a one-form symmetry. Okay, so I'm going to stop with the examples of one-form symmetry now and conclude with a discussion of an interesting application. Well, there's also the magnetic version. Remember we saw, for instance, in 4 dimensions that when we gauged some of the center, we got some back. I think a good rule of thumb is that if you're in a gauge theory that has a center, you have one-form symmetry, but you might have it from other places as well. Two-form symmetry is somewhat less common. One place where it naturally arises is in 6D field theories, because there you have two-form fields about. So a free abelian two-form field has a, if it's self-dual, has a U1 two-form symmetry. So that's the free case. And then the interacting case will give you some Zn two-form or something like that. So that occurs in interesting examples as well. You mean what wraps it? Oh, they're codimension 3, that's right.
In this case, the Zn guy, suppose I have a Wilson line in some representation R, then the phases will pick up will depend on the anality of that.
That's exactly right, yes. Yeah, the anality measures the center. Yeah. That's why this was k over n, because this is k boxes here. Yeah.
So it behaves exactly the same way with Wilson lines, but the four-dimensional Zn.
Yes. Yeah. Yeah, the 2-0 theory has the interacting AN 2-0 theory has Zn two-form symmetry. Yeah. How do they come about in string theory? Sorry, but an immersed M2 brane is codimension 3, right? So I think it's probably related to that. Okay, so I promised to do one application, so you see that this is not all formal language. We're actually going to do something with it. So we're going to study phases of 4D SUN Yang-Mills, and this discussion will follow a paper by Gayotto, Kapustin, Komorgodsky, and Seiberg.
Before you get to this example, you indicated that Generalized theory has, in fact, has these one-form symmetries, and the fact that you can work with the language of one-form symmetry to use for anything?
Yes, absolutely. I told it to you in the infrared topological, in a topological field theory, but the place where it's sort of the most potent and not just a rephrasing of things that you already know is in Chern-Simons matter theory. So suppose you want to discover some new duality in Chern-Simons matter theory. It's extremely useful to first make a list of the zero form and one form symmetries in the UV Chern-Simons matter description and their anomalies. And then if you make a conjecture that it flows to some gapped phase, you have something to look out for.
And this is not just summarized by saying that the gapped phases have to be either the same Chern-Simons theory or level entry. I mean, that will not automatically account for it.
Well, no, I mean, if two theories are the same or level rank dual, then of course they have the same symmetries.
Oh, but you're saying that is the same as the UV itself.
Yeah.
That is the non-trivial.
Yeah, that's the non-trivial thing, right? So, right. Suppose you're not even trying to check some first order transition. You're just trying to find the IR directly.
And give me one context in which this is useful in terms of this.
I think, well, I first used it in studying these SON Chern-Simons matter dualities and various bells and whistles thereon. So trying to study the phase diagram for adjoints or trying to things of that nature. Yeah. Yeah. So there's that, and there's also a similar paper by myself and Nadi and Hoshen about what happens with various different gauge groups that aren't SON, like spin N or ON or things like that.
In SUN, let's say with adjoint matter, was there something non-trivial to say?
I think there's something non-trivial to say. So for instance, in SUN with the adjoints, depending on the parameters, you might you might flow.
I haven't looked at SO and SUN. That's what it is.
Yeah. Okay. Let me give you a. Let me see if. Okay, but even in the dualities in the theories with fundamentals, in some small range of parameters, when they get sufficiently small, you flow to a Grassmannian phase. You do some spontaneous symmetry breaking, and there I think it's a useful constraint on the geometry of the sigma model to find all the one-form symmetries there. So it constrains the various homotopy groups of the sigma model, for instance. They also occur in gapless theories. So if you have a Chern-Simons matter theory, we think of it as to first approximation of the Chern-Simons plus the matter. And so we first list the one-form symmetry in the Chern-Simons theory, and then we see which part of it the matter breaks. And that's the part that's a true symmetry of the UV, and we have to find that if it has an anomaly, for instance, we have to find it at all phases. It could be conformal, that's right. Okay, so good. So let's look at the phases of 4D SUN Yang-Mills. So I'll flash the Lagrangian for you. Yeah, please.
You said that the existence of these symmetries has to be persist on the RG flow.
Yeah.
And in some situations you said you found anomalies, and those anomalies also have to be.
Mm-hmm. That's right. Yeah. So it can. I mean, if you find.
And the anomaly is just the answer.
So the good. So roughly speaking, if you have in 3 dimensions, you can have systems with 0 form and 1 form symmetry. That's the generic thing. And then there are, roughly speaking, 3 anomalies that you have to contend with. One is the anomaly purely in the 0 form, the ordinary symmetry, which we talked about. The second is the anomaly purely in the 1 form. That's the braiding of the abelian anyons. And then there can also be mixed anomalies. And those have to do with taking a junction of ordinary symmetry defects and braiding an abelian anion around the junction. You might get a phase when you do that. And that also persists on the flow. So it can be, if those structures are sufficiently rich, it can be quite constraining. Okay, so we have this well-known Lagrangian. Well, I guess maybe in Euclidean signature, depending on what signature we'll put in I. Okay, so what will our goal be? Our goal will be to uncover some anomaly in this theory at some value of theta. That's our first step. So the theta angle is periodic with periodicity 2 pi with these normalizations. And the first observation is that at specific values of theta, there's an enhanced symmetry. So at theta equals 0, 4 pi, there's time reversal symmetry. That's clear because time reversal symmetry acts to change the epsilon tensor to minus itself, so it changes theta to minus theta. So at theta equals 0, you're invariant, and at theta equal pi, you're invariant because of this identification. Okay, so now it will be straight. So we have this symmetry. We also, of course, have the Zn one-form symmetry. We're doing this form of the group. So we also have Zn one-form symmetry for all theta. So the claim is that there exists a mixed anomaly at theta equals pi between T and the Zn one-form symmetry. Okay, how do we see it? Well, we now have the tools to see this conclusion immediately. So a mixed anomaly, what does that mean? It means if you gauge one, you break the other. So since we now know what it means to gauge the Zn one-form symmetry, let's do that. So gauge the Zn one-form. What does that do? That takes us to SUN mod Zn gauge theory. And as we just discussed, for this global form of the gauge group, there are fractional instantons. With instanton number uh, 1 over n is the minimal unit. That's right. So the periodicity of theta is now 2 pi n in this normalization. And if we go back over here, it's clear that that means that we've broken T symmetry. Because at theta equals pi, T was a symmetry precisely because of this identification. So T is broken.
You should be able to see the other way around as well, that we gauge T.
It's more subtle to say what it means to gauge T. It means, but yes, so to gauge T means you consider your theory on a non-orientable manifold. That gets a little technical for me, but I think it is possible to see, but I don't know how to do it directly. If theta were, what? Pi n. So we could in this gauge group analyze the symmetries, and there could be a time reversal symmetry here, but there isn't the one form symmetry. It's a different symmetry. So relative to this theory, we see that there's a mixed anomaly. Okay, so we actually get an immediate conclusion. Well, before I say the conclusion, in case people are interested, there's this inflow action. How does it look? Integral over a 5 manifold. Again, we've got some two form ZN gauge field BB, and then we've got W1 of X5. This is the first Stiefel-Whitney class. That's the obstruction to the manifold being orientable. It's like the time reversal gauge field. Okay, so we get a nice conclusion. Which is that at theta equals pi, SUN Yang-Mills cannot be trivially gowned. Because there's an anomaly, and the infrared has to reproduce that anomaly. Okay, so now let's conclude by discussing some possible phase diagrams. And this will involve us making some speculative assumptions. Okay, so how can we match this anomaly, right? The infrared, we know that anomalies have to match. We found an anomaly, so the infrared has to have it. So there are, roughly speaking, two possibilities. The first is that all the symmetry is unbroken. So here I'm sitting at theta equals pi, and I'm asking what happens in the infrared. So all the symmetry could be unbroken. And if that's the case, that means the infrared should at least be a topological field theory, or maybe some interacting theory. And that sounds pretty implausible. So let's reject that hypothesis. Well, so certainly the idea that the infrared is interacting, well.
Okay, interacting meaning like it's implausible.
That's right.
Okay, that sounds implausible. But what about the deflection?
Yeah. Well, maybe there could be a topological field theory, and I guess at theta equals pi, we don't have strong lattice evidence, or any lattice evidence really, one way or the other. So I think that I'm just going to reject it because it will look more exotic than the first possibility. But we can put a question mark here. Well, let's try and draw a phase diagram, assuming that doesn't happen. So it is going to be speculative, this part.
I mean, we know at large n is there.
Right, but a lot of the mystery is for, say, SU2.
Okay.
Yeah, and then, but yeah, so at large n, that's right, at large n, we know it doesn't happen. At large n, I think we know that T is spontaneously broken.
You know, there's an old paper by which in 1960, somebody, I'll give you 1 minute time.
Yeah.
Okay, it starts off with wording this as a paradox. That how can you have a theory? Okay, see, the Stokes coupling is G squared. Okay, now, but if you make this, you know, in terms of theta, so we've got 1 by G squared and 1 by n. Okay? So the theta dependence of the torque coupling part is like theta by n. So in the torque limit, ordinary torque analysis tells you that things should depend on theta, like theta by n. Okay, just like that should be the dependence. Okay. However, that seems to be in conflict with the fact that theta is periodic with 2 pi. Because theta changes by 2 pi, theta by n changes by nothing. How can you have something that's periodic with 2 pi and yet be independent with theta by n? And his resolution to this was to say, well, suppose what's happening is that you've got some multi-valued function. Your potential in terms of theta was a bunch of potentials that look like this. Okay, so I'm going to have to get time. I'm going to clear up the paradox. Maybe after this. The point is that you will have to have the way these two could coexist. I can't do that. The way these two could coexist is that there were bunches of potentials like this, and that theta you make the space transition from this one to this one. So you get a first order phase transition. You can solve for that. How you give that back.
Right.
Is that you got these first order phase transitions, and therefore spontaneous breaking of the line, because you've got two equal minima, two different minima of the same, and any other point here, you've got an infinite number of competing possible minima, and you choose the lowest one, and exactly at theta equals pi, these two minima become together, and then you get a first order transition from this branch of the potential to this one. It goes on. I'm sorry.
That's fine. Okay, so the other possibility is that some of the symmetry is broken. If symmetry is broken, it's easier to match an anomaly. For instance, if we break the zero form symmetry, it means that we can match the anomaly by something living on the associated domain wall that separates the two vacua. So here we could have broken T or the one form symmetry. And now I'd like to advocate that this is what happens, at least under some plausible hypotheses. This is what happens, and this does not happen. This is not broken, that is. So as Shiraz was just reminding us, that's what indeed occurs for large n.
Sorry, if you don't mind.
Go finish, yeah.
Okay, so torque analysis tells you that each of these functions, n squared times f of theta by n. Now to make it periodic in theta, the only reasonable possibility is it's n squared plus f of theta by n
Summed over
all the
orbits.
So n squared times n is equal to minus infinity to infinity f of theta minus 2 pi m by n. Okay? Now we know that this f function here has a minimum at 0, just because theta and minus theta are the same by time. Right, so it must start quadratically at 0. But now since this is by n, okay, you only care about this function at very small values here. Okay, so this is the same thing. So there's some constant which we don't care about, let's throw it away. This thing is some number times a quadratic function. You say it could have a quartic and a sextic and so on, but since the argument is very, very small where we're going to access it, because we're going to access it near theta over 1, we only care about the quadratic part. So basically this function, just on general analysis, on general ground, some number which we can't determine times f of theta minus 2 pi m by n, the whole thing squared, sum over n. Now, the great thing is that this n squared and this n squared cancel. So that the whole thing is just sum over m theta minus 2 pi m the whole thing squared. So this general analysis tells you that the form of the effective potential as a function of theta is this. So now just plot this. So there's this, there's this, there's this, there's this. So if you're wait for theta equals 0, you go to the lowest energy guy. All these other branches are higher energy. Please stay here. But at this point, you make a phase transition to period. Okay, so you've got this point a first order phase transition between two competing things. And this was borne out in ADS. I think this is another pure one. I've only written obsessed about SUN, not even sure what it is.
Why is it some holomorphic effect?
Forget holomorphic. Just let's look at, forget the angle stuff. The thing is theta equator. Okay? Now, you get a torque limit by making your whole action n square center. You have to write n, trace is already in. You need an express. You have to write n theta trace equator by n. So this torque transfer, forget everything. Tells you actually better theta. Yeah, I mean, it's one of these brilliant little things. You use nothing to get the answer. This is the answer to the effect. After a number, you use nothing.
It has to be a function of the Stokes standard convention, which is theta by n, and it also has to be
Periodic.
So
Think
you
very
make
other
an
way.
immense sum.
Yeah.
So every theta has to be equal to theta minus 2 pi over 2 pi n, and it's somewhere.
You see, the point is you could have had a function that was periodic with 2 pi n. But that is, it's impossible for it both to be periodic and to be a function of theta. Periodic is, so that is the only way that it could have it is it's a sum of different branches. So then each function is analytic in theta. But the sum of different branches would be the periodic. And then, because of the large n, it's just quadratic. And so, this is the answer.
The function is this function of theta by n. Is it also, I mean, the n also shouldn't exist directly, or is there anything take this theta by n times n and make it theta equal to theta n? This is not anything.
No, in large n counting, it's n squared times the function of theta by n, no other.
No, there was no other theta in that formula.
There was an n square outside and theta by n.
Minus m over n. 2 by m over n.
No, that was put in by hand. You see, the basic function is a function of theta by n. And then you take that function and make it periodic in theta with 2 pi. That is that. So, but that is what you compute from summing is that basic function.
Okay. Good. So let me, at least at large n, we know this is true. Let me also comment about what it would mean to say that this symmetry is spontaneously broken. What is it? We didn't discuss spontaneous breaking of higher form symmetries, but we could have. Let's briefly say what it means for this one form symmetry to be spontaneously broken. So I claim that the Zn one form symmetry is spontaneously broken. That this is actually a language for saying that the theory is deconfined.
So this is a theory.
Hmm?
And you've not put it in a circle.
No. I'm just talking about yeah. This is at 0 temperature. We will soon discuss the circle, but okay. Why is this statement true? Well, remember that the charged objects are Wilson lines, and a symmetry is spontaneously broken if a charged object has an expectation value. Okay, so imagine a large Wilson loop. If that large Wilson loop has an area law, then the theory is confining, and for large enough size, the expectation value goes to 0. So then we would say that the symmetry is unbroken. Conversely, if the symmetry is broken, then a charged Wilson loop will have a non-area law expectation value, and so the theory will be deconfined.
The insertion of a Wilson loop, if it was unbroken, the insertion of the Wilson loop would be zero. Because, and that would be the factor.
Yeah.
So there's a polytopic version.
So this is, as an aside, this is a nice way of saying, re-seeing old facts about when you can invariantly say that a theory is confined versus Higgsed, that it's closely related to the center symmetry and so forth. This is a way of saying that in terms of symmetries. Okay. Okay, so we believe that, let's take as gospel that at 0 temperature, the theory confines for all values of theta. So we want this to be preserved. Okay, so then a natural hypothesis supported by large N is that this symmetry is spontaneously broken. And we could imagine that that continues even all the way down to SU2. Okay, so let's make a little plot that will start to enhance as time goes on. So here will be temperature. We've gone all the way down to 0. Here will be theta. It's 2 pi, 0, pi. And at theta equals pi, we think that there is a first order phase transition where we, from here we have 1 vacuum, here we have 1 vacuum, and here we have 2. Okay, so if we extrapolate up a little bit, there's some first order line that comes out of here.
So this is like the delta point in between. I mean the one.
Exactly. It's at that same point.
You have a double basically.
Mm-hmm. Okay, so this is the first order T breaking line. Okay, and so we'd like to know what happens as we move up. Okay, so let's make some comments about that.
About the 0 temperature hour theory, what you have concluded is, if there is no topological conformity theory, and if there is not an interaction conformity theory, and if there is no breaking of the Zn center symmetry, then time reversal symmetry has to be.
That's correct.
Okay, so some information, but not a lot. It's based on a lot of.
It's based on a lot of hypotheses. That's right. Yeah. Yeah. And that's right. I mean, this is just based on all of those plausibility arguments. Yeah, there are lots of ways to match that anomaly. I mean, for SU2, you could imagine it's not really known, so you could imagine that here it's just deconfined. And that would be another way of matching the anomaly.
That would be
Yeah. So, right. Okay, so good. Let's briefly discuss what might happen at finite temperature under all of these assumptions that Shiraz just outlined. So, right, so let's put the theory on a circle. And let me list the symmetries that we get for SU2. Much of the discussion will carry over, but let me just do SU2 for simplicity. Okay, so we know we have a Z2 one-form symmetry. So we're going to look at the effective 3D theory and try and say what its symmetries are. So we know we have a Z2 one-form symmetry. And we now also get a Z2 zero form symmetry. That's because when you take a one form symmetry and you put it on a circle, you get both a zero form and a one form symmetry.
In particular, Z2 one form, zero form symmetry is finite at this particular test concept.
That's right. And we will obsess on it a little bit here. Yeah. Okay. If theta is 0 in pi, we have this Z2 one form symmetry again. And now here we get Z2 times Z2. Okay, so one of the Z2s is again the reduction of the one form symmetry. The other one comes about from the fact that if you have a time reversal symmetry in 4D, then when you reduce one down one dimension, it becomes a unitary Z2 symmetry, because you can take the reflection part to happen in the compactified circle. So it will just look like an internal symmetry. Okay, so these are the interesting unitary symmetries. And what does this mixed anomaly look like? So the here, this one. So if you have in 4D, if you have a Z2 one form symmetry, more generally, if in D dimensions.
Well, this is 3D.
Yeah, that's right. These are 3D symmetries. Okay. So the reduction of the mixed anomaly pairs these three together at theta equals pi. So remember that it involved the time reversal and two of the one form symmetry pieces. So the time reversal comes down and becomes one of these Z2s. And then we pick up one of the 3D one form symmetry and this Z2 zero form symmetry. So the reduction of the mixed anomaly tells us that at theta equals pi, yeah, so in 4D it was something like W1 BB.
Right.
Now we're going to integrate this on a circle. So this will become the Z2 unitary symmetry here. If this has two legs in the 3D space-time, then it will become this. But then to make up the rest of the integral, this has to have one leg in the direction that we compactify on. And therefore it becomes a zero form symmetry. So the reduction of the mixed anomaly tells us that at theta equals pi, the simplest assumption is that at least one of these Z2s is always broken. Okay. So or there could be topological theory, et cetera, et cetera, et cetera. So at high temperature, as I'm about to say, we really do know what's going on. So at least at high temperature, it'll be clear how this is satisfied. But it's possible for lots of exotic things to happen at low temperature. So I'm just going to sketch under the assumption that you never find the topological field theory or interacting conformal field theory. What might the phase diagram look like? But that's actually, a subject of some debate.
For SU2 at exactly the deconfinement temperature, it's believed that there is a...
It's a second order. Yeah. It's a second order transition. That's right. Yeah.
So at least at the deconfinement temperature.
Yeah, we're going to draw this.
This.
Yeah, we're going to draw that. Right. So this will be for SU2 even. Okay, so let's first say, just as a review, what we know is happening at high temperatures. So at high temperatures, so then you can study the theory by dimensional reduction. So you get SU2 gauge fields in 3 dimensions plus one adjoint scalar. And it's convenient to parameterize things in terms of this Polyakov loop. integral around the S1 of A, which is the same as e to the I beta phi. Trace. Okay, so what do we know? So we know that at high temperatures, an effective potential is generated for this, which has two minima. So phi, which has minima at u equals plus or minus 1, say. Good. So now, under the zero form center symmetry, this is a fundamental Wilson line. This is a Wilson line, so we can say how it transforms. This is the Adrien-Wilson line. So under the zero form center symmetry, u goes to minus u. So therefore, this expectation value breaks the zero form center symmetry. And so this is the deconfinement transition. So at very high temperatures, we know that the zero form symmetry, zero form Z2, I guess I should call it, we need to give them different names. One is related to T from the 4D, and this one is related to the center. This is broken. Okay, and you can also check that the other symmetries are unbroken. So, for instance, at high temperatures, we can integrate out phi at a very high scale, and then we're in the SU2 3D theory, which confines. That shows us that this symmetry is always unbroken, even at high temperatures. So if we have a Wilson loop in the spatial directions, it has an area law. And T doesn't act on this. So the Z2T doesn't act on this, so that symmetry is preserved.
And we know that very much of the Z2 3D theory, that SU2 3D theory was very much a scalar, does not have any non-zero topological theory.
Well, maybe we can add that to our list of hypotheses. I think that's a pretty reasonable assumption. But right, so up here, you can see how this constraint is being satisfied. So up here, this is the only symmetry that's broken. The other two symmetries are unbroken, and that's consistent with this, that we need at least one to be broken. Now, in SU2, as we lower the temperature, these two minima will come together, and eventually this symmetry will be restored. And it's actually believed that this is a second order transition. Which is therefore in the Ising universality class. So this is the Ising model here. Because it's a second order transition governed by two minima coming together.
You know, another way of saying it is that the order parameter that becomes light is this. Okay, and this U has eccentricity.
Yep.
It should be described by scalar field theory in a vector symmetric fashion.
Yep. Okay, so then this becomes the mysterious region here. And you can make lots of hypotheses for what happens there. If you are interested, you could read the last 20 or so pages of that paper that I mentioned. But let me just say that this anomaly tells us one thing about what's going on here. So what's going to happen? So this line could end somewhere, maybe at a second order point. Could end here, or could end above here, or exactly at this line. Maybe something interesting happens. And we can say one interesting thing, which is that the temperature for T restoration. So let's look at theta equals pi and see what happens. Must be greater than or equal to the temperature of the deconfinement transition. Why is that? So imagine this was false. So then we have a picture that maybe looks like this. Something happens. And now here, all the symmetries are preserved. That violates the anomaly. So this is an inconsistent diagram. No. It has some, no. I mean, I drew it in a way that, what? At theta equals pi. This is at theta equals pi. Because that's where we have the anomaly. So it constrains a little bit the possible ways in which this second order phase transition can merge with this first order phase transition. But there are lots of possibilities that are left open.
For what happens above?
For what happens above, or or maybe they terminate. Maybe it's equality. It's you can speculate quite a lot, and it's just not known, even with all the assumptions that I made. Okay, so let me stop here.
Is the reflection symmetrical or theta equals pi?
Yes, because the theory does have time reversal symmetry. It just has a mixed anomaly involving time reversal symmetry.
Everything has to be set as SUN.
I think in SUN, this is not supposed to be second order.
Right.
So
But what is it? Does it?
I think the only thing no, this inequality still is true. The only thing is that it, specifically for SU2, because this is second order, you can envision more wild things that might happen in here. I think it's just known to not be second order at large n, right?
No, better not. You see, suppose you've got theory governed by an order parameter that is ZNC.
Oh, I see.
Okay.
Yeah.
Now, you can ask, do you know of any conformity? It's a second order, but there must be a conformity theory with ZN.
Yeah.
Do you know of any conformity theory with one relative operator with ZN? The answer is no. However, you do know conformity theory with
U1 symmetry.
U1 symmetry. So it could be that the Zn gets accidentally enhanced to U1 at that point. Okay? Now when will that be consistent? That will be consistent if in the pairing U1 symmetry, namely the
O2 and all. Yeah.
the lowest operator that preserves Zn but not U1, namely phi to the n. Okay? If that were the case, then it's a consistent scenario. To speculate that you get a second order phase transition with U1 symmetry. Now in n equals 3 okay, the phi cubed operator which preserves Z3 but not Zn happens to be right. Okay? So for SU3, you know that unless there's a conspiracy, it cannot be U1 symmetry. There just isn't actually. Actually, it turns out for SU4 and higher, the phi to the 4 or phi to the n is irrelevant. So there, it could have been the planar exponential, but lattice evidence strongly indicates.
Lattice evidence at theta equals 0.
As
Yeah.
it is.
Yeah. And do we know at large n?
Yes, you know.
have to say, I don't actually, I've heard that argument about the irrelevant operator before and, the O2 model and so forth, but couldn't it be that we just don't know most 3D conformal field theories?
It could be, but it would have to be a conformal field theory with one variable. These are rather, it's harder to believe you don't know. It's easy to believe you don't know conformal field theory from two. So these are weird.
Okay.
Okay, but because you're interesting by choosing one thing
Mhm.
in your vector.
Yeah.
Okay? And it could be, but then that's really a surprise, because why haven't better people ever encountered this? Because one
It's,
relative.
zero symmetric model and this very essential real function.
You say, so you want symmetric, so you turn on, let's say, phi to the n. Yeah, you generally just get.
You generally just go back.
Not quite the end. Because it's a domain.
Yeah.
Yeah.
Firstly, phi to the n is hard because a Z2 theory, of course, is like a real theory. Okay, so in order to have the phi to the n at all, you want to be the U1.
Is there any, is there a way to suppress the anomalous dimension of monopole operators?
Which one?
I'm imagining a different theory, a different conformal field theory with U1 global symmetry, where the U1 is some monopole number.
Ah.
I mean, again, typically we expect that monopole operators to high power also have large anomalous dimensions, but
I do. Anyway.
yeah.
Yeah. Okay, I mean, this is not a watertight argument.
Yeah, well, none of this was worth.
But it suggests this,
Yeah.
and it's sort of interesting with the lattice frequency exactly.
Yeah.
It really